So I'm going to be talking about toric and tropical Bertini theorems. And this is joint work with Francesca Gandini, Milena Herring, Fatime Mohammadi, Jenna Rajchgot, Ashley Wheeler, and Josephine Yu, some of whom I see in the audience, so they can keep me honest and also answer your questions in the chat. So feel free to direct any difficult questions to my co-authors. So here's the cartoon version of the talk. We have the classical Bertini theorem. We have the toric one. So this is a subtorus here, twisted cubic t squared t cubed. And here's a tropical one. This is a very cartoon version because my artistic ability being somewhat limited, my pictures are actually breaking some of the dimension requirements we'll have later. But the idea is most people, if you will know the classical Bertini theorem, and we're going to generalize that in two different ways in the talk. Okay, so that's the picture version. Let me say it again in words. So we remember the classical Bertini theorem says if we have a projective variety that's irreducible over an algebraically closed field, and the variety is at least dimension 2, then we can slice it with a general hyperplane and the result will still be irreducible. So the idea is that the set of hyperplanes in projective space for which the intersection of x with the hyperplane remains irreducible, that's going to be dense in the dual projective space. Okay? And I mean, this is a sort of totally fundamental result, key for induction proofs. And in a way, it's so fundamental that if there are beginning graduate students, sometimes I know when I was first learning this, I think people often don't even bother mentioning that they're appealing to Bertini's theorem when they appeal to it, because it's just such part of the oxygen. So we know it's useful. So what I want to talk about in this talk is two variants. So there's two ways we want to generalize this. The first is we're going to change H and change that to a torus. So instead of having a subvariety of projective space, we'll have a subvariety of an algebraic torus. And instead of intersecting with a hyperplane, which you can think of normally as a smaller projective space, we'll intersect with a subtorus. So that's the first variant. That's the toric Bertini theorem. And then the second is if I start with, I'm going to replace x with its tropicalization. So instead of having my algebraic variety that I intersect with a hyperplane, I'll have a tropical variety that I intersect with a hyperplane. And we'll say a little bit as we go through about why we would want each of these. Okay, so that's the plan. Classical Bertini, we're going to change in two different ways. Okay, and so let me start with the toric version. So I'm going to start with a subvariety of an algebraic torus. So for me, Tn will always be my notation for the torus. It's going to be isomorphic to k star to the n, so split here. And I'm going to replace the h, the hyperplane of Bertini's theorem, by a subtorus T prime. But this is where we run into a problem. The problem is that we can't expect only a few bad subtori. Okay? I mean, waving my hands, in the usual Bertini theorem, we only expect a few, you expect a general hyperplane to be good. When we start talking about subtori, you already have the problem of what do we mean by general, but we definitely can't expect only a few of them to be bad. And this example is meant to be an elementary example to explain this. So we'll start with the hypersurface x squared minus y times z squared in a three-dimensional torus. Okay? And you can see from the y is enough to let you see that this is irreducible. This actually is itself a subtorus, but we won't worry about that for now. I'm going to intersect with the two-dimensional subtorus T1, T2 squared, T2. Okay, so x intersect T prime is just the variety of, I just plug in T1 for x, T2 squared for y, and T2 for z. And so I get T1 squared minus T2 squared times T2 squared, or T1 squared minus T2 to the fourth. And this is just a difference of two squares. Okay, so I can write it as the variety of these two other smaller, a subtorus and a coset of a subtorus. Okay. So that's an example of a bad torus, right? That's an example of a subtorus where that you slice with your variety and you get something that's reducible. Okay. But my point is, and this is what the bottom of the slide is showing, is that actually, in a certain sense, you expect most subtori to be bad. I've written it as T1 to the A, T2 to the 2B, T2 to the C, but you could actually even change this T2 to a T3 and go with a sort of but if we have T1 to the A, T2 to the 2B, T2 to the C, for any A, B, and C, we're going to have, we intersect X with this T prime, you'll get the variety of T1 to the 2A, T2 to the 2B plus 2C. Again, you can see it's a difference of two squares. The variety is going to have two components. Okay, and here's the problem, right? This was for arbitrary A, B, and C. So in a certain sense, so it's not the case that most subtori are good. Okay, and we could change this one. Okay, so that's the problem when you start to generalize when you start to try and generalize the Bertini theorem from the classical setting to the toric setting. So maybe I should pause for any questions or. Okay. Luckily for us, this had already been solved. So this approach, I think, starts a work of Zannier, but the version I'll tell you about is essentially the version of Fuchs, Mantova, and Zannier, though maybe I'll soften some of their hypotheses slightly to make the presentation easier. And here's the general idea. The general idea is that we're going to rule out this problem. Okay, we're going to rule out what was going on here, and we're going to say actually the problem here was that exactly that on the previous slide, we could have done on the previous slide when I could have had a T3 here. I could have had essentially switching by an isogeny. So let me give you the definition, and then we'll see what it means on this example. So we say that pi satisfies the property PB, that's for pullback, if for every isogeny mu from TD to TD, the pullback is irreducible. Okay, so isogeny is a surjective map with finite kernel. So essentially it's going to be given by a monomial map like this, x comma y goes to x comma y squared. And we've got the pullback of, we've got pi from x to t to d, we've got the isogeny from t to the d to t to the d, and we're asking that the pullback be irreducible. Okay? And we want that for every isogeny. It turns out that if E is the degree of this map because I'm saying it should be finite, if E is the degree of the map from x to t to the d, it's enough to do the isogeny that takes every variable to its eth power. So you do only have to check this once. This is a condition that you can check, even though I've said for every isogeny. This is a condition that you can check in finite time. And we can see that the example I gave you on the previous slide does not satisfy this condition. Okay, why? Because if I take the isogeny x comma y goes to x comma y squared, well, in the pullback, we can just essentially substitute in y squared for y, and we get again x squared minus y squared z squared. Again, we've got this difference of two squares, and we know it's going to be reducible. Okay, so these, in some sense, one of their observations was to say this failing this pullback property is the problem. And while I won't go into it, there are plenty of examples that do satisfy the pullback property. So it's not the case that every variety and every projection and like this fails this pullback property. Okay, so any questions, comments? Okay, so what we're going to do now is say the theorem of Fuchs, Mantova, and Zannier is to say, okay, suppose I have such a projection, so I have a dominant finite map of from X onto T to the D, and it satisfies this pullback property. Then the claim is that there's only a finite union of bad subtori. And those bad subtori, it's such that if you're not, if your torus is not contained in one of those bad subtori, then the pullback, so then the pre-image is irreducible. And you can think about, the way I often think about this is maybe X is contained in T to the N, you've projected T to the N to T to the D, so the pullback of T prime is itself a subtorus of your ambient space that you're intersecting with. And so we're saying in any subtorus of this form, the intersection will be irreducible. And we're actually saying slightly more than that. We're actually allowed to put a coset of my torus. So this theta will be a coset of the torus. This is the difference in, if I was giving a sort of affine in Bertini theorem, between intersecting with a hyperplane passing through the origin and an affine hyperplane. It's the difference between a subtorus, you know, maybe x minus y and x minus 5y. So we've got so we're allowed to take cosets of the torus too. And the idea is finite number of bad subtori. If you're not in one of those, then any coset, the pre-image, is irreducible. Okay, so that's the Fuchs-Mantova-Zannier Toric Bertini theorem. Yeah, that's useful. In the paper where this is in JABS a few years ago, they have many, well, this is actually a corollary of one of their main techniques, and they have many other different corollaries. However, the one problem for my applications is that the paper was written for k equals c, and the proof required characteristic 0. Okay? And being on the combinatorial side of algebraic geometry, I do not want to see a characteristic assumption unless I can actually see a real reason for it. Because most things, particularly in tropical geometry, we have very few things that actually depend on the characteristic. So you want to somehow, I want to understand, is this really a characteristic 0 result or is it not? They wrote the paper just over the complex numbers. If you look at the proof, it requires characteristic 0. There's some resolution of singularities and also some aspects of Galois theory that are requiring characteristic 0. And at least the majority of the paper, this is really intrinsic. Okay, this is not one of those stories that if someone comes along tomorrow and proves resolution in characteristic P, then we remove the characteristic assumption. Okay, and I'll maybe just say a few words about that because this is a sidetrack, but I think it's neat, so I want to tell you about it. What they're actually, one of the punchlines of their paper is to prove is to sort of give up a solution to the following problem. Suppose I have a polynomial in two variables, x and y, and it's monic of degree d in y. So viewing it as a polynomial in y, it's monic of degree d. And you want to say to yourself, does this have a polynomial root? So the question is, if this polynomial f of xy, if this has a root y equals g of x, where g is actually a polynomial in f, can you bound the number of terms of this in terms of d? Okay. And it turns out in characteristic 0, the answer is yes. And that's one of the punchlines of the FMZ paper. And in characteristic P, the answer is no. Okay, so at least, that's sort of the strong evidence that at least a large part of their techniques are not going to extend to outside characteristic 0. Okay, so some of what I want to tell you about in the rest of the time is a different approach to this Toric Bertini theorem that which doesn't require characteristic 0, so works over an arbitrary field. Okay, so maybe any other questions, comments at this point? Okay. So before I do that, though, I want to tell you about my personal motivation. I mean, why did I come to a Toric-Bertini theorem? And that's because what we wanted was actually a tropical Bertini theorem. So the idea of tropical geometry is we're looking for a combinatorial shadow of my variety. And so I'll tell you just in a few lines the version that I'm going to be using here. So we're going to start with a subvariety of a torus, and where here my field K should be algebraically closed and a valued field. Okay? In general, we can relax some of these assumptions, but I'm giving you the version that makes the exposition simpler. So the tropicalization of X is going to be just the closure of the valuation of X as a subset of R to the N. What do I mean by that? Well, a point X in X, because I've chosen coordinates here, I've chosen the X as a subvariety of K star to the N. A point in X comes as X1 to Xn. The Xi are elements of my field. So I can take the valuation and I get the valuation of X1 up to the valuation of Xn. That's a point in R to the N. And so if we do this for every point in the variety, we have a collection of points in R to the N, and I can just take the closure in the Euclidean topology. So that's the tropicalization. So this is the shadow part. We're taking the shadow of my variety under the valuation map. And it's a theorem, goes back originally to Berry and Groves in geometric group theory, so 20 plus years before tropical geometry existed, and then with extra pieces added by Bogart, Jensen, Speyer, Stempfels, and Thomas, and Cartwright and Payne, that says if X is irreducible, the tropicalization is the support of a connected polyhedral complex that is pure of dimension D. So polyhedral complex means a union of polyhedra that intersect nicely. By the support, I mean I only care about the points in here. So these two polyhedral complexes where I've gone from one to the other by just subdividing are the same. And I want it to be pure of dimension D, means all of my maximal polyhedra have the same dimension. So these are examples of one-dimensional polyhedral complexes. Okay, so Berry and Groves essentially proved that it is the support of a polyhedral complex and of the dimension bound. And then the work of Bogart, Jensen, Speyer, Stempfels, and Thomas set up the approach to connectedness, and Cartwright and Payne actually finished the proof and gave the conception. And the proof to connectedness was essentially take the tropicalization of your irreducible variety, take trop X, and slice it with the tropicalization of a generic hyperplane. So they essentially deduced this connectedness from the fact that curves are connected and the fact that we have the classical Bertini theorem. Okay. However, intersecting the tropicalization of a hyperplane is a slightly more complicated combinatorial object, and understanding it is not as easy. So they actually asked the question of, did they have to intersect with the tropicalization of a hyperplane, or could they have just intersected with a hyperplane? And then that's something that when Josephine, you and I were thinking about generalizing this connectedness property, that we also needed. And we needed it badly enough that we actually looked into proving it. So this is a theorem, so of Josephine and mine and characteristic 0, and then the rest of the team, so Francesca, Milena, Fatime, Jenna, and Ashley, added for arbitrary characteristic. And this is the idea that I can take, maybe I'll explain it first by waving at the picture. I can take a tropical variety, so this is a picture of a standard tropical plane in R3, and I can intersect it with a general hyperplane and expect to still get the tropicalization of an irreducible variety. Okay, so what are we saying? We're saying if we have a tropicalization of an irreducible variety of dimension d at least 2, then the set of rational affine hyperplanes in Rn for which the tropicalization of, for which the intersection of sigma with H is the tropicalization of an irreducible variety, that's dense in Euclidean topology on projective space. So again, we need some way of knowing what we mean by hyperplanes being near, and we're just saying, let's think about them as rational points in projective space, in the dual projective space. Okay, so, or you could rephrase this again and say, yeah, in any way you're in your space of hyperplanes, for any hyperplane, you can wiggle it a little bit and get something whose intersection with the tropical variety is the tropicalization of something irreducible. Okay, so that's a fairly close analog to the classical Bertini theorem in the tropical setting. And we want it for the same reason that we want classical Bertini in the usual setting. Okay, so questions, comments at that point? If no one asks questions, I am a little worried that I will I'll end far too early, which maybe you don't worry about, but we'll have to see how it goes. Okay, so far we've now seen all of the characters from the cartoon at the start, right? Classical Bertini theorem that you already knew, the toric Bertini theorem, and a tropical Bertini theorem. Okay, a reasonable question, though, is to ask, what do these have to do with each other? So the connection is that the tropicalization of a subtorus is a hyperplane. Okay, so an affine rational hyperplane is the tropicalization of a coset of a subtorus. So let me show this to you in an example. If I have the hyperplane 4x plus 5y minus 3z equals 1, that's the tropicalization of the coset, the variety. Well, it is the tropicalization of the variety of x to the 4th, y to the 5th minus alpha z cubed, where the valuation of alpha equals 1. Okay, if you tropicalize a binomial like this, you say, I need the valuation on the left to equal the valuation on the right. That's 4 times the valuation of x plus 5 times the valuation of y should equal the valuation of alpha plus 3 times the valuation of z. Okay, so 4x plus 5y equals 3z plus 1. Okay, and now you think to yourself, if there wasn't the alpha there, this would exactly be a subtorus, and it would exactly be a subtorus, for example, parameterized as t1 cubed, t2 cubed, t1 to the 4th times t2 to the 5th. For any t1 and t2 in K star. Okay, and then we're taking a coset. I'm multiplying this by, hopefully I got my algebra correct to say a 4th root of alpha, comma 1, comma 1. There's more than one way, obviously, to write this as a coset. And times the subtorus should give you this hypersurface. Okay, so whenever we have a hyperplane, it is the tropicalization of a coset of a subtorus. And this is, from the tropical perspective, why, if we go back to the Bertini theorem, we had these cosets here. So I had a subtorus and I had a coset, theta times t prime, that I wanted to intersect. And this is why this is very useful from my point of view. Okay, so we have the subtori, we have the cosets. Okay. So this means if my alpha is sufficiently general, here sufficiently general means in a more non-Archimedean sense. So it's a statement really about being the image of a translative alpha in the residue field being general enough. The tropicalization of x intersect this coset will be the tropicalization of x intersect h. Okay, so roughly for general enough alpha, this is saying that tropicalization commutes with intersection. You do need some sort of genericity statement here. This intersection might be reducible, but it's only going to be reducible in a kind of mild fashion. All of the components have the same tropicalization. And that's why, in the tropical point of view, we don't have to worry about this PB, because somehow the problem with PB is dealing with these isogenies, and that in a tropical sense, that doesn't change the tropicalization. So, I mean, these are just some hand-wavy sentences. The point is to say we can reduce this from the Toric Bertini theorem. So up to some details of getting rid of the PB assumption, and you can see that if I would like to say I'm going to choose my T prime to make this irreducible, and I slice, and I know that it's, if this is irreducible, then this intersection is the tropicalization of an irreducible variety. Okay, so that means we can automatically get the tropical Bertini theorem already in characteristic 0 from the Fuchs-Mantova Zannier theorem. However, this did not seem, from the tropical perspective, like it should be a statement that depended at all on the characteristic. And so this was after Josephine and I had finished the paper. So Francesca, Milena, Fatima, Jenna, Ashley, and Josephine and I were all together at BAB at a Women in Commutative Algebra workshop, and we decided to think about removing this characteristic hypothesis. So what I want to tell you about now is a different approach to the Toric Bertini theorem that holds in arbitrary characteristic. But so again, I think my next slide is a change of thought. So again, this will be a good point for any questions or comments, and either via the chat or out loud. I do sort of encourage people, please do interrupt if you have a question or a comment at this point. Okay. Well, while we're waiting for people to type their comments in the chat, let me state. So I said a Toric Bertini theorem on the previous slide because I'm going to state it slightly in a slightly variant fashion. It's good. I mean, this is we're going to start with an algebraically closed field, and now if my projection for x to t to the d is a finite dominant map satisfying the pullback property, then we're claiming that the set of t prime with intersection for which the preimage of the coset of t prime is irreducible for any coset. So the set of such t prime, I claim that that's dense in the space of all tori. So how do I want to think about the space of all tori? Well, one way is I mean, this is an intrinsically discrete set of data, but I can think about this as rational points in this Grassmannian. Okay, one way to think about that. I mean, I come from a tropical perspective, so I think to myself, my tori are, when I tropicalize the subtorus, I get a dimension of t prime dimensional subspace of the d-dimensional space, so a point in the Grassmannian. But yeah, there are other ways to think about that. Okay, so and again, the point is, you give me your subtorus, you say I don't like it, the preimage is reducible, I can tweak it to a nearby one, and then say, hey, you can also take any coset you like of this nearby one, it will still be irreducible. And just to give you some concrete example of this, if I take this example, so this is, if I take x being this hypersurface in 4 space, so my variables are going to be y, t1, t2, t3. So I take the hypersurface y cubed plus 1 plus t1 plus t2 plus t3 in characteristic 2, and I project onto the t1, t2, t3 coordinates. Then if I take this one-dimensional subtorus of the form t to the a, t to the b, t to the c, where A, B, and C are your favorite integers, then the preimage is irreducible unless A plus B equals C. And this example and the subtorus are actually cooked up to be exactly explaining what goes wrong in, I think, if I come back to, I think I told you here that with Fuchs, Mantova, and Zannier, they were worried about bounding degrees of roots of polynomials was when f is monic of degree d, and it turns out if you take these polynomials here, if we take this polynomial here, once I've plugged in this, so if I plug in t to the a, t to the b, t to the c into this, these are exactly the polynomials. You'll then have a polynomial in y and t, which are exactly the bad polynomials in characteristic 2. However, if we move it slightly away from a plus b equals c, then we no longer have this problem. Okay, so that's what we're saying is that the Toric Bertini theorem, at least in this form, we can't quite give the finite number of bad subtori, so it's a little weaker in that sense, but in the sense of saying you have a torus you don't like, we can move it a little bit and get a better torus. For many applications, it will, well, for our applications it is as good, and I believe for many other applications it will be as good. So that means we're removing the characteristic assumption. So let me give you some idea of the proof and the way this is going to go. I mean, I have to admit, I tend to turn off in ideas of proofs. This slide is going to be a overview which justifies why we're going to jump into considering one point, and then that point will be again another re-entry point into the talk. So let me do those reductions to justify, which is just justifying why we're going to talk about what will otherwise look like a completely different topic for the next few slides. Okay, so the first point is a fairly easy reduction to the hypersurface case. So we can assume that x is actually a hypersurface given by one polynomial f in t1 up to td and y, and we're just projecting onto t1 up to td. So that's exactly the situation we were in here, where we're projecting. We had a hypersurface and we projected onto t1, t2, t3. Okay, so that's the first point, reduce to the hypersurface. Second point, we could also reduce to considering that my subtorus is one-dimensional. Okay, that means we're going to, the question becomes, for which vectors in z to the d, if I do the substitution, if I take f, which was a polynomial in t1 up to td and y, but I make it a polynomial in x and y by just substituting in ti is x to the ni, so we have f of x to the n1 up to f of x to the nd, comma y. This is now a polynomial in x and y, and we're asking, is this irreducible? Okay, because we want to know, that's the same as saying, is the intersection with the subtorus t to the n1 up to t to the nd irreducible? Okay, so we're getting, well, sorry, is the preimage rather of the subtorus t to the n1 up to t to the nd irreducible? So we now have this question. It's a question just about about hypersurfaces, and we're going to specialize d of the variables to one variable. And now the next step is, let's view f as a polynomial in y with coefficients in, and it looks like when I was editing this, I removed some subscripts. This should say the field of rational functions in t1 up to td. Yeah, so we're basically saying, take your original polynomial y, don't think of it as living in the Laurent polynomial ring, think of it as living in as a polynomial in y with coefficients in the field of rational functions in t1 up to td. Okay, go ahead. I mean, we're pretty good about thinking of polynomials in one variable. Factor it. Your alpha I are going to live in the algebraic closure of the field of rational functions here. And so the bulk of the proof is to think carefully about a field that contains the algebraic closure. Okay, we can't go quite as far as describing the algebraic closure, but we want to think carefully about a field that contains the algebraic closure and do that in a way that works in arbitrary characteristic. Okay, so that's the approach. So what we're going to do, I'm going to do for a few slides now, is think about this. Okay, so again, questions, comments? Okay, so this is another re-entry point to the talk, because we're going to back up and talk about something that, again, a priori seems unrelated. And that's essentially what I just motivated, which is let's think about the algebraic closures of fields of rational functions. So you may know, well, many of you will know that if in characteristic 0, if I want to take, I can always use the Poisson series as a vector. So the algebraic closure of rational functions in one variable is contained in the field of Poisson series in as long as k has characteristic 0. So another way of saying that is if f is monic in y, f being a polynomial in 2 variables, then if I factor f, I could always factor f as the product of y minus alpha I, where the alpha I are Poisson series. So Poisson series, again, are the union of Laurent series in x to the 1 over n. So you think of them as Laurent series with fractional exponents where you always have a common denominator. Okay, so this n will, so any given series has a common denominator, but maybe the common denominator for one is 100 and the one for another one is 1,000,000. I want to caution here that there is a convention choice, because this will become relevant when we go to more variables. So we could also have, it was a convention choice to take the positive exponents. So this is, I mean, somehow in one variable, this is something that we either never think about or it gets swept under the rug really quickly when you're first thinking about, even about sort of Taylor series, etc., or back in the day, right? I mean, and I've just tried to illustrate this with this example. If I think about 1 over 1 minus x, you want to say as a power series that's 1 plus x squared, but you could have chosen instead, if working with usual power series, to work with power series that only have negative exponents. So the equivalent of the Laurent series would only to be allow a finite things to go a finite number of positive sides. So you could also write this as minus x inverse minus x to the minus 2 minus x to the minus 3. Okay? If you've never seen this before, this should probably be one of your take-home points from this talk, which is just, multiply this by 1 minus x and check that you get 1. And well, let's hope I didn't get a typo as I was preparing the slides, which is always a danger. The point is that there's a convention choice. You choose the power series and then go to take the algebraic closure. So we're choosing which direction. And that convention choice is really a direction. Are we going in the x direction or the x inverse direction? Okay. Questions, comments, or maybe corrections if you have some side errors here? Okay. So that's characteristic 0. Characteristic P, Poisson series are not algebraically closed. Okay, so Chevalier pointed out that the polynomial, and again, I was modifying something, so I may have introduced some side errors, but y to the p minus y plus x inverse has no root in the Poisson series. So I can think about it as being a polynomial in y with coefficients in the field of rational functions of x. In characteristic 0, Poisson series contain the algebraic closure of, they're an algebraically closed field containing the field of rational functions, so it would have a root, but in characteristic P, and sorry, here I should have said K, if K is a field of characteristic P here. So in that case, Chevalier pointed out that there is no root here, and then Abianca said, well, actually, if I go to a different field, then I do get a root. So what we can say is, instead, the problem is, well, so what are the roots? So you get for each I, and then you get this piece, which is the sum of from 0 to infinity of x. And actually, so I think, did I mess up? Oh, no, I can't remember whether I've got a typo. That should be a 1. But we've got x. Actually, I think that should start at 1, perhaps. And then we've got x to the 1 over p to the I. So what's going on is, for example, if p is 2, you've got x to the half plus x to the quarter plus x to the 8th plus x to the 16th. Your exponents do not have a common denominator. Okay? In the Poisson series, exponents have to have a common denominator. Here, in Abianca's series, we've got it no common denominator for our series. However, the only bad exponents, the only bad denominators are powers of p. And in general, it turns out you can form a field by allowing series in x with exponents of the form m over n p to the I. And then now that we're not making things, now that things are no longer as discrete, you also introduce a well-ordering condition. So you want your set of exponents to be well-ordered and only have exponents of the form n times p to the I, where n is going to be fixed for a given series. That's like the Poisson thing. But the p to the I can be unbounded. So you'll get things like, this is a p equals 2 case. My n is 3 in this example. So I've got x to the a third plus x to the 1 and a 6th plus x to the 2 and a 12th plus x to the 3 and a 24th. And you can see that my denominators are all of the form 3 times 2 to the something. Okay, and that's the condition. And I've also, well, I artificially spread them out so I didn't have to worry about the well-ordering condition. But in general, if we didn't do that, we'd have to also demand that the set of exponents that showed up is well-ordered. And that's necessary in order to get a well-defined ring. Okay, otherwise, you run into trouble when you try and multiply series like this. Okay, so that's characteristic, that's single variable case. So that's been known for, I mean, I guess around, actually, I didn't look up the time, but this is fairly early work of Abianca, I think. So Chevrolet quite a while. So the one variable story has been well known for quite a while. And the summary is what? In characteristic 0, we just have a finite bound. And in characteristic p, we have to allow powers of p in the denominators of our exponents. If I go to more variables, then this is where we see two things going on. The rules about the denominators are essentially the same. So the denominators are all allowed to look like n times p to the I, where n is fixed for a given series, but the p to the I can go up. And now the series, all of your exponents in your series have to be in a given cone. Okay, so this is in one variable. There's only 2 cones, right? You've got 2. If we're in R, there are 2 possibilities for cones. There's the positive reals and there's the negative reals. Okay, and that's why on this slide here, I had my 2 choices here. So the idea is also in one variable, you have 2 choices for, you have 2 choices for what algebraically closed field you're going to construct that contains the field of rational functions. And in more variables, you have even more choices, and the choice is not just plus or minus, it's a choice of a polyhedral cone, a pointed polyhedral cone where the supports live. And there's a few more conditions. I'm sort of trying to give more of a flavor rather than giving exactly all the technical details. So this is some of the first things in characteristic 0. This appears, I guess, a bit over 20 years ago in work of MacDonald. And then a bit more recently, this was also work of Saavedra. I think in both cases, it was essentially their PhD theses. So MacDonald is characteristic 0. Saavedra is extending this to characteristic P. Okay, and just to give an example, if my cone is the positive orthant, and here I've got P as 2 and my other denominator bound is 3, this would be an example of what I mean. Again, and again, there is also a well-ordering condition that it's related to the cone. But so we're going to have something like 1 plus x plus y. You can see the exponent. You get so 1 plus x plus y plus x to the third y to the half plus x to the third y to the quarter plus x cubed y to the eighth. And you can see in all cases, every denominator that's showing up is a multiple of 3 times 2 to the something. Okay? And all of the exponents are living in this cone. So that's, and it turns out if you have series satisfying that there's a certain extra well-ordering condition that I've left out, you can construct those series will form a field that is algebraically closed, and this is the work of McDonald and Saavedra, etc. And it contains the field of rational functions. In this case, in my example, it will be the field of rational functions in the variables x and y. Okay. So, okay, so what did we do? We needed these fields because if you remember, I said we were going to reduce to the fact that we had a polynomial in y that we were going to, and t1 up to td that we were going to factor as if it was a polynomial in y. So we wanted roots in the algebraic closure of t1 up to td, and what we needed though was we needed something that was slightly smaller than the field constructed by McDonald and Saavedra. And so our contribution, and I'm being a bit vague here because it does get somewhat technical, but we're going to construct an explicit algebraically closed field containing the field of rational functions, and it has a subring, which I've done some rough analogy. My subring R, it's going to be a subring with field of fractions, our field, and you should think about it as loosely like a valuation ring. So it's loosely like the power series inside the Laurent series, or the integer is inside Q. And that ring, on that ring, there will be a well-defined specialization map. So we'll send Ti to x to the ni. Okay, and that's going to be like intersecting with a subtorus. And we needed some extra conditions. We needed a smaller field because when I do these sort of specializations, that's like taking a cross section of this cone. Okay, if you set, if I set both x and y to be t, then I'm just adding up all of the exponents that live here. And the problem is that in these fields, you might be adding up an infinite number of terms, so there might not be a well-defined function. So our field has the property that when you do these sort of specialization maps on the appropriate rings, the appropriate subring, then there is actually a well-defined specialization map. Okay, so why did we want that? Let me just finish by coming back to the proof. We had a hypersurface in a torus. We're projecting it down to a subtorus. We factored, and this was all stuff I told you before on the outline of the proof slide. We can factor f as a product of y minus alpha I, where the alpha I are now in our new field. Our new field is again, it contains the algebraic closure of T1 up to TD. And we can actually, if you scale appropriately, you can, you stretch things out and you can assume that actually the alpha I are in the subring R. And that's like clearing denominators. And then suppose I have a subtorus in T to the D. That subtorus has the form T to the N1 up to T to the ND. Then the pre-image of that is actually the variety of f to the x1 up to x to the nd and y. And this is just a specialization of f. Under the specialization map, I discussed on the previous slide that sends ti to x to the ni. And so now you ask yourself, well, if I take a polynomial in t to the t1 up to td and y, and I substitute powers of x for the ti's, when does that factor? Well, it factors exactly if I look at this, if I take a subset, a proper subset is actually a polynomial, okay? Because over the big field, over the algebraic closure, of course, it factors completely into roots. We're interested in, does it factor in polynomials? Well, that's going to happen if the product of some of your y minus roots is itself a polynomial. Okay, so we want to know this factors if the specialization is a polynomial. And now that's only, and now I guess the trick is to check that because of the control we have on the field, that's going to only happen, sorry, that won't happen for almost all subtori. So you're going to have, you look at the specialization and essentially you say, hey, I've got this term t to the 1 over 100, as long as, you know, as long as I don't set t1 to x, as long as n1 is not 100, this is not going to be, I'm not going to end up with an integer. And so we're not going to get a polynomial. So the idea is somehow you get a whole bunch of, in particular, you get some index conditions. You get, it's that the exponents have to, your n1 up to nd must live in some sublattice if this factors. And from that you see that most tori are going to be okay. Okay, so that lets us prove the toric Bertini theorem again. So maybe I'll just finish by putting up again this theorem. This lets us prove again this theorem, our toric Bertini theorem, which is the variant of the FMZ1 in arbitrary characteristic. And from that, we also remove the characteristic assumption on the tropical Bertini theorem. So you can see we've got the toric and the tropical Bertini theorem both interlinked, and both interlinked by this surprisingly still fairly open question of understanding the algebraic closure of the field of rational functions. So maybe it's a good place to stop.